beginning of the notes, you'll see there's 3 different easy examples of finding derivatives. And if I find this derivative, I get 2x. If I find this derivative, I get 2x. If I find this derivative, I get 2x. So all 3 equations have the same derivative, which just makes it a little tricky when you're finding the antiderivative and you're trying to go back to the original. It's a little confusing on like which one of those, like how would you know what your antiderivative is? But the only difference between these 3 first equations is the constant at the end. And so the big thing with antiderivatives is recognizing that every single constant has a derivative of 0. And if you have the derivative and you're trying to go back to the original and you have like a 0, so to speak, you don't know which constant is part of the antiderivative. Each of these antiderivatives, like here and here, this is a vertical shift of a graph. So all of these have the same shape graph. It's just a matter of what the vertical shift is. This is a regular quadratic. This is up 9. This is down 2. So when we're doing an antiderivative, we're trying to figure out the original function, and we just have to keep in mind that there could be a constant at the end. Okay, so first of all, a little bit of vocabulary. All 3 of these words mean to find the antiderivative, or there's this symbol, which looks like a long S. It's kind of fun to actually practice writing it. Looks like this. So if you have that with a dx at the end, whatever's in the middle, that's the equation that you're trying to find the antiderivative of. So you might have these symbols, or you might have a word that says integration, and integration means antiderivative. Or you might have a word that actually says antiderivative. So any of those in the directions mean to do the same thing, which is to find the antiderivative. And here's our answer. So 2x equals x squared. The plus c at the end represents the constant. Remember, every constant has a derivative of 0. So then that plus c is just a generic representing any constant. It could be plus 9, it could be minus 2, it could be whatever number. After you take your antiderivative, the symbols disappear. So like these go away, and then my answer is just this. A little bit more of notation. If you have an integral of f of x, sometimes when you get your antiderivative, it just might be shown as capital F of x. Or you might have an integral of an antiderivative, which would just give you back f of x. Of course, you're going to have plus c in every problem that you do. But I kind of call this like a context clue, just depending on what the directions are, like just being careful about knowing how to label your question and answer, depending on the way that they label the function in the directions. Okay, differential equations are equations that use dy and dx in them. So all of the problems we're doing today are going to be a differential equation, or in other words, a derivative, because you're going to have dx at the end. And our goal will be to find the original or antiderivative. Okay, we're going to start out first before we do any official rules, just kind of thinking through these ones. And so I want you to kind of think ahead of what do you think this original was? And hopefully you can think about, oh, well, that would be x cubed originally, because the 3 as a power moves down to the front and becomes that coefficient. And then I subtract 1 from the power. And then a little bit more difficult. So this is x squared. That must have come from x cubed, just like the last one did. But since there's not a 3 in front, there must have been something here to cancel. So that would have been a 1/3 there. And that way, when I bring my 3 in front, the 3 and the 1/3 cancel and subtract from the power and gives me x squared. And then on this one, same idea. I have an x to the first here, so that came from an x squared. But when I brought the 2 in front, I must have had something to cancel with, which would have been a 1/2. So kind of thinking through is the same process of what you do for your actual formalized rule, which is that you're going to add 1 to the power, like all these are 1 power higher, but then you're going to divide by the new power. Add 1 to the power, divide by the new power. And so taking a look at the second row, if I think about that process, this is -2. The original must have had a -1 there, because when I take the derivative, I subtract 1 from the power. And then there must have been something going on in front here to make this change to be a positive. So it's -1x to the -1 plus c. That's the same thing you would get if you just added 1 to the power and divided by the new power, because it would end up being a -1. So this would be y equals -1 over x plus c. Here I think of this as x to the -3. And so to go to my original, I would add 1 to the power. Then think about what was in front to make that cancel out. If I divide by the new power, that helps me figure out like what would cancel out. So -2, if I bring that in front, would cancel out, and then subtract from the power to get the -3. Okay, and then last, if you have cosine, your original must have been sine. Hopefully that's an easy one. These power rule ones are kind of tricky. So let's put a formal rule to that. This is your big power rule. And this means add 1 to the power, divide by the new power, plus c. So add 1 to the power, divide by the new power, plus c. And underneath here is a list of all of the different derivative rules we've done. I know you did several rules quizzes about these, so hopefully you can quickly glance over this list and be like, oh yeah, I remember most of those, because we're about to do the opposite of all of those. So the one we just mentioned is here. This has a u in it instead of an x, which is okay. It's the same rule. U is the variable of the expression. That says variable. And then n is a number. So this is for like if you had x to the 7th or something like that. So that's the rule we just talked about. But there's a whole bunch of other rules, and we're only going to do like the top part of these rules today. The first one is if you have a constant times a function, you can bring the constant out front and then just do the integral of that function. The second one over here is that if you have 2 integrals added together, you can just do them separately, and that's fine. And then the third one's a little tricky. There's like an implied 1 in here. So the antiderivative of 1, you would normally think of that as x. But since this says du at the end, we're putting a u there. Like du, this tells us what the variable of the expression is. So if this had said dx, this would have been x plus c. 1 over u is going to go to ln of u. And that's because when we did logarithms, it went to u prime over u, derivative over original. E to the u just goes to e to the u. A to the u. Okay, so in this case, a is the number. U is the variable. And so this integrates to 1 over ln a to the u. So look, kind of starts out looking like that same power rule, but it's just different because this would be used for something like x to the 5th, and this one would be used for something like 5 to the x. Okay, then the last rules we're going to talk about today are these trig rules, the ones that we kind of already know, or are the reverse of the ones we already know. Going backwards, you have to be careful about your negative signs. Anything that you integrate, if the answer starts with a c, is negative. All the integrals that start with a c are negative. Oops. Okay, let's try some rules out. Okay, so number 1, this is a power rule. The equation I'm looking at is here. I'm going to add 1 to the power, divide by the new power, plus c. Once I've done the integral, I drop this integral sign and dx. It's almost like parentheses around your problem. You just drop that off because I've done that operation. Number 2, same thing. Add 1 to the power, divide by the new power. Here I'm going to add 1 to the power, divide by the new power, which will cancel those 2's out. And then 3 will go to 3x plus c. So the constant will just go to the constant times whatever the variable is. 3 looks like a quotient rule, and we do not have an antiderivative rule for quotient rule or product rule. So we're going to actually split this up. I call this bunny ears. So I'm going to rewrite this as x squared over x squared plus 1 over x squared, which that simplifies to 1 plus x to the -2. And I'm continuing to write my integral symbol because I haven't done an antiderivative yet. I have just simplified it. But now when I do my antiderivative, 1 goes to x, and x to the -2 goes to x to the -1 over -1, or in other words, x minus 1 over x plus c. And then number 4 has a radical sign in it. So before I integrate, I'm going to change this radical to be an exponent. And then just do the power rule. Add 1 to the power, divide by the new power. And when I go to do 3/4 plus 1, I think of it as 3/4 plus 3/3. So I get x to the 7/4 over 7/4 plus 1 will go plus x And then last on this one, I would reduce this fraction by multiplying by the reciprocal. So this becomes 4/7 x to the 7/4 plus x plus c. So because of dividing by a fraction, it's like a keep change flip. If you want to skip that middle step, you can. You're allowed to go straight to do 7/4 times 4/7. Okay, fifth example looks like a chain rule. We do not currently have an integral rule for chain rule. So instead, I'm going to have to multiply this out. Oh, oops, it said t. Okay, so 2t minus 1 times 2t minus 1. If I multiply that out, it's 4t squared minus 4t plus 1. So I'm going to integrate 4t squared minus 4t plus 1 and just use the power rule. So I'm going to get t cubed over 3 for that first one. So 4/3 t cubed minus. And then I'm going to get t squared over 2, which will reduce the 4 that's already there. So the dividing by 2 is just going to give me a 2 there. And plus 1 will go to plus t. Kind of skip showing that middle step because of work, but this was like squared over 2, which cancels with the 4. Okay, then on number 6, we start getting into some trig stuff. So the first one is just power rule. That's t cubed over 3. But then the sine rule, sine goes to negative cosine. Because whatever the integral is, if it starts with a c, it's negative. So sine goes to negative cosine. But there's already a negative here, so it turns into plus cosine. Number 7 uses theta as the variable instead of x. So this is going to go to theta cubed over 3. And then secant squared will just come from tangent. And we just have a theta in our answer instead of x. Like I can see that theta is the variable. Number 8 looks like a product rule, but we're not going to do a product rule because we don't have a way to do that with integrals. We're going to have to distribute this. By the way, we will learn a way to undo product rule, quotient rule, and tangent rule. It's like an entire process. Okay, so integral of secant tangent becomes secant. Integral of secant squared is tangent. Let's see. Okay, number 9, first of all, you cannot do bunny ears upside down. That is not allowed. We're not going to do that. Also, when you look at this one, if I was in your shoes, I might think, oh, that bottom part factors. So possibly you might think of doing this and make it 1 plus sign, 1 minus sign, but it doesn't reduce anything. Like you don't end up being able to cancel anything out. So even though that's like a good thought, that doesn't end up working. So the thing you're going to use here is a trig identity. So if you remember that sine squared plus cosine squared equals 1. And if I solve that for cosine squared, I get 1 minus sine squared. So if I put that back into my problem, this becomes cosine squared. Okay, then I look at the sine over cosine, and hopefully you can look at that as well and think of that as a tangent. Sine over cosine is tangent. But if I make this be tangent, there's still a cosine on the bottom. And so I kind of think of that as a 1 over cosine. Cosine on the bottom is the same thing as a secant. This gives me secant x tangent x. And I've done a bunch of identities, but I've yet to do the integral. So I'm still continuing to write my little scrolly s down. So I took the identity here, made it cosine squared. Then I took the identity of sine over cosine to make tangent. And then I took the remaining 1 over cosine to make secant. And the integral of secant tangent is just secant. So this is secant x plus c. Okay. Number 10 is an a to the u rule. And it's that rule because I have a constant on the bottom and a variable as the power. So this goes to 1 over ln of a times a to the u plus c. So a is 7 here. And so I'm just going to do my rule with 7. I'm going to switch to another color just because this is getting so jumbled down here. So this is going to go 1 over ln of 7. A to the u is going to be 7 to the x plus c. And these are multiplied together. So if you'd like to write the 7 in the numerator, you can, or you can just leave it there at the end. 11 is e to the x, just goes to e to the x. That's the easiest one there is. And 12 is also a rule. So this is hard to catch on at first. If you were to try to do this one without the rule, you'd start like this and you'd say, oh, if I add 1 to the power and divide by the power, I get a weird answer. Dividing by 0 doesn't work. So like that doesn't work for power rule. Instead, this goes to ln absolute value x plus c. I believe this is rule number 5. Let's see. Yeah. So I had 1 over u in this formula. The problem we did had a 1 over x. So it would just go to ln x instead of ln u. You do have to keep your absolute value in there. So make sure you have your absolute value and of course plus c. Okay, then last we're going to look at if you were to look at the directions here, this means to find the original and plug in the ordered pair. And so your answer will not have a C. You're going to actually figure out what C is. Okay, so I'm given that this is my derivative. I want the original. Here's the ordered pair. Okay, so put an integral symbol, and I'm going to distribute this. So I have my derivative inside an integral symbol, which means I'm going to do the antiderivative. I get x squared, because I just bring this 2 back up, add 1 to the power, divide by the new power, minus 2x plus c. That gives me my original, but that is not the specific solution. That's a solution with a plus c in it. To get the specific solution, I have to use my ordered pair. That's x and that's y. So I'm going to 2 equals 3 squared minus 2 times 3 plus c. So 9 minus 6 is 3. And then if I subtract 1, c works out to be -1. Now your answer is not c equals -1. Your answer is the equation that you got with the c value plugged in. So this would be your final answer. It's your specific solution. On the next one, we're given a second derivative. And so to solve it, to get the original, I'm going to have to do the antiderivative twice. So let me start with, that's my second derivative. Antiderivative of that, add 1 to the power, divide by the new power, gives me x cubed over 3 plus c. So that equals f prime. That's not my original, that's just my first derivative because I've only gone like 1 antiderivative. Then I use this ordered pair, that's a little prime right there. So I plug in 0 for x and 6 for y. And it turns out that c is 6. So updating my equation, I get x cubed over 3 plus 6. Okay, so that's my first derivative. Then if I want to go to the original, I have to integrate again. So add 1 to the power, divide by the new power. If you already have a denominator, you can just multiply the denominators together. So dividing by 4 there makes 12b the denominator. 6 will go to 6x plus c. Then I use this ordered pair, which is also 0, 6. That's going to give me my original. So 0 plus c equals my y value of 6. So c is 6. And I just update my equation with 6 in there. So x to the 4th over 12 plus 6x plus 6. That's my final answer for original. And on this last one here, this is second derivative is sine x. So I'm going to do the integral first to get my first derivative. Sine goes to negative cosine. And that's just a rule that antiderivative of anything that starts with c is negative. And then I plug in the order pair 0, 1. So 1 equals negative cosine of 0. Quick reminder that in the unit circle, 0 is an angle, and the ordered pair there is 1, 0, and that's the cosine value and the sine value. So cosine is 1 here. So cosine of 0 gives me 1. There's a negative out front, which makes it -1, so c works out to be 2 if I add the 1 over. So my first derivative is negative cosine x plus 2. I'm going to integrate that to get my original. The integral of negative cosine is going to be negative sine because cosine goes to sine and I carry the negative with it. And 2 will go to 2x and I put a plus c at the end. And I totally ran out of space here, so I'm gonna move over here. Okay, so I'm gonna plug in the 0, 6. I have 6 equals negative sine of 0, and then plus 0 plus c. Sine of 0 is also 0, so I end up with just c equals 6. Sorry, that's hard to read there. So I have negative sine x plus 2x plus 6, and that's my original equation answer. Y equals. Oh, goodness. Okay, this is y equals negative sine x.